Okay, I should probably not blur the background if we're going to use the whiteboard today. Cool, we'll try this. Hi, Dante. Hopefully you can see everything. Let's try this. And Dante, please interrupt us if you're just getting the presenter view as opposed to the wonderful slides I prepared. Silence is golden, unless you're muted. Okay, how's everyone doing? No one caught on fire, that's good. Or at least no one that I see. Everyone looked at the homework? No, you looked at the homework? Looked at the homework? You don't care. That's smart. Okay. The first one is not complicated. It's just asking us to do something different than what we did in class. And the second one, you use both of those things. The third one, you have to take the file that I put on Canvas and read it into Excel. You can use the line fitting from Excel, the built-in one. I don't expect you to have computational physics for this. And then the last two have more to do with planetary interiors than they have to do with rock ages. Cool. All right. Don't know what that is. My own moon. How can you tell us a moon? How do you know it's not a studio in Hollywood? Yeah.
A reflection?
Reflection what?
His mask.
Yeah, reflection of his mask is pretty good. So you can see the guy taking the photo. That's pretty cool. No atmosphere. So not on Earth.
Could be darker.
Could be dark room. That's true. Could be dark room. Yeah, this is lots of conspiracy theorists, but of course, if it was moving, one of my favorite things is like in the absence of air, all footprints are preserved. So as we talk about erosion processes when we get to the Earth, you'll see that every footprint that was left on the moon is still there, unless it's been destroyed by micrometeorites or as the spacecraft is flying away. And that's the cool thing if you watch any of the videos, right? Like they walk around and there is no like if you were to walk around in a dusty place on Earth, you'd see like every step. You don't see that here. Okay, I forgot to update these. This is not what we're doing yet. I was gonna add a couple things in the front here. We're gonna finish up our discussion of planetary interiors, and then we're gonna talk about cratering, and then we're gonna get into the moon, which has examples of both of these. So ignore that. That'll be updated. Should be this. This goes after. Okay, cool. Questions before we start? Okay, so we wanted to bring our brains back into calculus land. So how we break up a sphere into manageable pieces so that we can understand how the mass is distributed. What was the moment of inertia? How do we interpret that word? Okay, what type of motion? Resistance to rotation, right? Right. So mass is what is mass? What is inertia? I know. That's why I'm saying it again very slowly and not answering.
Oh, I didn't answer what is mass. I know what you mean by that.
Okay, so the question is, if force equals mass times acceleration. We've said this a million times, but if you were to explain it to a child, the idea of mass, right? The first thing you think of is weight. And of course, that's wrong because that's a force. But you have this inherent feeling about what mass means. So something with more mass is something there's something intrinsically different than something with less mass. So how do I contextualize, understand the concept of mass? What is mass? Sure, but can't everything have a force? I mean, electrons can have a force on them. Photons have a force on them, and they have no mass. How do we intuitively understand mass? Right, remember we just said that was wrong. But weight is telling you deep down about something about it.
Strong or how easy it is.
Right, how hard or easy it is to move. And so the inverse of that, the way to think about this, is that mass is resistance to change in motion. So if something is moving already, and it's very massive, it's hard to change the motion. Similarly, if it's not moving, it's hard to get it started, right? That is the definition of mass. So similarly, this word inertia, right, is that resistance to change in motion. But here we're talking about rotational motion. Okay. Now we're awake. All right, good. So let's decompose the mass into chunks so that we can treat them like point masses in a tiny infinitesimal piece. And we talked about this already. We said dm can be broken up as dm, which is an infinitesimal piece of mass, is just rho dv. And we showed that earlier, right? Where rho is constant basically over that, so we don't have to do the chain rule. Okay, and then we integrate them, right? And if, for example, the density changes as a function of your spherical coordinates, that's perfectly fine because rho here can be a function of all of your spatial coordinates and the integration will work, right? Okay. So in Cartesian coordinates, we write it like that. And in spherical coordinates, we write it like this. And I'm not going to derive these, but you can find these in the back of any book. The place that you'll want to look, if you are not remembering where they come from, is your vector calculus book. And if you don't have one, happy to lend one to you, because I have too many. Okay, here's the spherical coordinates pieces. So in 3D, where we all live, hopefully, XYZ is my right hand, like this. And you can see the geometry here. If I want to talk about a distance r that is from the origin to some point XYZ, then I construct a couple different triangles. So I construct a triangle here, which I can relate through trigonometric functions. And then I create another right triangle here. And the combination of those two right triangles, this one and that one, gives us all of this really fun stuff. Okay. People lost by that? A little bit. Okay. So this piece here is that piece there. Right? So if imagine we put our XYZ, put it along X to start with. Okay, and then we can rotate it in the XY plane, back and forth. So that gives us the first piece of the puzzle, and that is this piece, this angle, the azimuthal angle, the rotation around Z, and then operating in the XY plane. Okay, so I start along X, and then I rotate it azimuth. So as long as sine theta is, or as long as theta is 0, you're not moving from the XY plane. What's sine of 0? What's that? Okay, so that's why we define this as sine of pi over 2. So you draw the azimuthal direction from the top of C. Okay, and you'll notice that each one of these becomes what you think it will. For example, sine of theta, right, is 1 when you're in the plane. We can only do that if you define it with respect to where the z-axis is. So it's pi over 2 or 90 degrees away from the z-axis. And then sine of pi over 2 or sine of 90 is 1. Good. So that disappears in these two. This one here becomes 0. So that's saying that you're not in z. You're only in xy. And sure enough, you're only in xy. And this is your standard x equals r cos phi and y equals r sine phi. And that's your standard polar coordinate conversion between x, r, phi. Right? Okay. So this piece is the easier one. This one, r, is your distance formula. So if you had some radial direction and you want to break it into your Cartesian, then it's just x squared plus y squared plus z squared, and that's your Pythagoras theorem in 3 dimensions. The trickier part here are your arctans. I don't want to show you those live, but those are reasonable. Okay. And this will all be in your notes. So here's your fundamental theorem of calculus. Who discovered the calculus? Newton, is that correct?
I don't know.
That's what they tell us it is. That's incorrect. The first derivation of calculus was a man named Isaac Barrow, not Isaac Newton. He was actually Isaac Newton's tutor. And the reason why Isaac Newton and Leibniz are both credited with the discovery of calculus is because they argued very loudly about who was the discoverer of calculus. And it turns out that if you just argue about who was right, you'll get much more publicity than the person who was right. But calculus comes from this right here. This is the fundamental theorem of calculus from which all other things derive. And that shows that there is a mathematical relationship between things like slopes and areas under the curve. So which of these two things is a slope? Bless you. Good, where? Here. This is by definition the slope of the function capital F. And which is the area under the curve?
Yeah.
The other one, very good. So this one here is the integral of f of x. This is the area of f of x between points A and B. And the fundamental theorem of calculus says that you can graphically represent these two functions. And if you do that, then they are connected. Right? You say that these are differentiable. Now we won't use like real math here, so we won't be talking about proving whether the function is differentiable or any garbage like that. Okay. But here's the things you'll need to know. Okay, and you can just go to this, right? This says that if I have a derivative of x of n, it's this. Take whatever letters you want. Derivative of x to the 4 is 4x to the 3. Ta-da! I don't need to know it. I just need to know where it comes from. Similarly, let's go the other direction. The integral of x to the 4, well, this is much more complicated. Now I have to put the 4 everywhere, right? That's okay. Okay. So that's the first one. That's the one that everyone learns to start with. This is the easiest one because you just got to write the same shit over and over. The only thing that happens is if you have any coefficient of your x, it comes out. Okay. And we'll use that, probably not in this class, but you would use that in, for example, fluids, or you'd use that in any time that you have an exponential, which are waves, for example. So you use that for the wave equation. Okay, these ones here, sines become cosines and cosines become sines. That's a fun one. And similarly backwards. Fun? If you use Wolfram alpha, you're doing a good thing. Why is that? Is physics math? No. Physics is not math. Math is math. Okay. Physics is about understanding why things do the things they do. The equations are not just letters and numbers and equal signs. When I said, what is mass? You should have an intuitive intuition of what it means. Explaining it in terms of other equations is not intuition. The math gets in the way. Okay, so you're focusing right now on creating a mental model. If I increase the mass, what happens? If I add this type of material in there, this mineral becomes present. This tells me something about the history, right? And the reasons for those are things that we can construct in a mental model. The math helps us do calculations, but the calculations are not the goal. The mental model is the goal. Okay. Algebra is obviously important too, but you can't have algebra. The Wolfram Alpha won't do the algebra, so that's fine. The calculations of integrals, calculations of derivatives, I think you'll notice in about 10 years, you'll look back on this time period and you'll be like, whoa, this must have been what it was like before people got calculators. And for a long time, people calculated logarithms by opening a book and reading out of that book to find the logarithm. Now you type it in your phone. Similarly, you will not need to know how to calculate integrals and derivatives in 15 years. People just won't do it. Unless you're a theorist. Okay. Oh my God, why does this never work? I can't spend too long on it. Okay, there we go. So let's talk about the moment of inertia of an undifferentiated sphere. So what is undifferentiated again?
No. So
Good. And what was the example I like to use for my ice cream? What? Cookie dough ice cream. So what is the state of the cookie dough ice cream?
it was mixed with that.
Good. So delicious still, right? Delicious, undifferentiated cookie dough ice cream. Okay. Unless you're like a weirdo and you like open it up and the differentiated, and then you take it from the top and you eat all the cookie dough and you put it back and you don't tell your mom. I'm not saying I do that. I'm saying someone could do that. I'm not saying I did that recently. I'm just saying someone could. Okay.
We said recently.
Whoa, I didn't say recently. Okay, all right. I'm on fire here. All right, so uniform density is important here. Let's use this in order to understand how an undifferentiated sphere, which has uniform density, those are the same statements, right? Right? Yeah. So the density doesn't depend on any azimuthal component. We're going to be working strictly in spherical coordinates here. And we have a relationship between m and rho. So we wrote this in the first class. We wrote that rho is mass divided by volume. That's the definition of density. Why does it say 3m on the top?
Volume.
And volume. What is volume? 4/3 pi r cubed. So the 4/3 comes up here and then the r cubed is down here, right? So this is just that. Good. All right, so rho looks like that in terms of m and r for any object. Okay, so now what we need to do is we want to discover what the moment of inertia of an undifferentiated sphere is through an axis about its center. Recall that I told you that the moments of inertia depend on the chosen axis of rotation. So because moments of inertia are resistances to motion, then the moment of inertia for this rotation that I'm doing like this versus this rotation that I'm doing like this, trying not to hurt anyone, versus this rotation, notice that those are 3 separate rotational axes, right? And you can then calculate which of those has the hardest resistance to motion, right? Okay. So here's your DI. And I said by definition, DI is this. DI, which would be the little tiny contributions to the moment of inertia, is going to be your R perpendicular squared times the dm. Well, we just said the dm up here, right? So we can just plug that right in. And that becomes R squared sine theta squared dm. Okay? Do we see why this is this? Well, this is this, right?
Yeah.
This is this. So our perpendicular is with use of our sine theta here. So because sine theta in this direction, right? R perpendicular is always R sine theta. It's going up. Okay. Okay. You want me to draw that or are you good? Remember that it's not perpendicular through the sphere. It's perpendicular to the axis of rotation. So if this R is going up in this direction, then R sine theta is if R sine theta, sorry, if the R that I'm choosing is going in this direction along Z. So let's work through this really quickly. Okay, so you have an object that's rotating like this, okay? And I'm only looking for the contributions that are going normal to the rotation axis. Rotation axis is up, down. If I have one of those arms that's aligned with the rotation axis, how much does it contribute? What? It contributes nothing because the sine theta here, right? What is theta when theta is 0? Or sine theta when theta is 0?
0.
0. Where's the maximum contribution?
90 degrees.
Right, away perpendicular from the axis of rotation. So if I'm aligned with the axis of rotation, I contribute nothing to the moment of inertia. What? Right, but that would not be aligned with, right? So like, let's take our arm. So this is the axis of rotation, and I can use my arm like this. I can point it in any direction. So if I'm looking at this contribution, right? There's a piece of mass up here, right? And it's pointed up and down. Is this piece up here contributing to the moment of inertia?
No.
No, right? Because of the R perpendicular. Okay, now we're getting it. Okay? Okay. All right, so now we can break up the dV part, the dm. So the dm is the rho dV. And I told you what dV was in the last slide. C'est bon? Oh my God, look outside. It's orange.
It looks like there's a different fire in that.
There's
direction.
3, yeah. There's one over there. There's
I'm saying this one looks like it's coming from right,
Oh, legal.
like a completely different.
Lake Elsinore has one. The whole fire map is crazy right now. I guess a week of 100-degree plus temperatures is not good for plants.
Not shaking the bone.
Yeah. Okay, so let's look at this now. So here's I, we're going to integrate. Okay, we're all really good at integration now. Since this is a 3-dimensional integral, we're going to integrate over R. We're going to integrate over theta. And we're going to integrate over phi. Okay, so the integration bounds. Okay, from R, I'm going to go from 0 to big R. That'll be the exterior. For phi, I'm going to go from 0 to 2 pi. But for theta, I'm only going to go to pi. Is that weird? Well, pi is like this, right? So why am I only going halfway for theta? Oh, very good. See, this is hand usage at its best. So let me just do that for folks online. Yeah, no, but I'm going to show it online first. So you make a P, right? And then you rotate all the way around. So once you've swept through 1/2, then you're going to go all the way around 360. And that gives you full coverage, right? Okay. If you go all the way around once, like that, then you need to rotate half. But if you do both, you're double counting. That make sense? So if you go 0 to 2 pi, 0 to 2 pi, you're going to be off by a factor of 2. C'est bon? Okay, we'll do it again. Here's your sphere. Okay, radial goes out like this. Okay, so let's take some sphere like that. If I want to fully describe every point, I need to sweep across every point. So let's take a fixed R now. Okay, here's my radius. As I move down like that, I'm going to sweep out a whole circle. So now I have a circle, right? Now, if I rotate that circle 180 degrees, every edge of that circle has now swept out the entire sphere. Right? Yeah. Another way of thinking about that is sweep this one down 180. Have a half circle. Now let it go all the way around. It's now swept out the whole circle. Well, you only need a half of it. Okay. C'est bon?
Yes.
Good. Okay, so that's the integration bounds, and here's all the scrap that we had from last time. So we have the r sine theta squared, that's this piece from the r perpendicular. And then the dm has all of these wonderful contributions. And since phi, as we said at the beginning, does not depend on r, theta, or phi, it's going to go ahead and come out of the integral. So the rest of these can be integrated, right? All right, good. Oh no. Okay, so someone can take each piece. Who wants this piece? Good. Who wants this piece? Boo! Who wants this piece? Okay, all right, you guys have to work together on this piece. Fastest talker always gets the easiest piece.
I feel like in Calc 2 or something, I did this at one point and I don't remember.
This one?
Just like sines and cosines with powers,
Yeah, it's
but I
annoying.
don't remember.
Yeah, it's annoying. How would you do it?
If I memorize it.
Oh my God, guys, what did I just say? No one's listening. Look it up.
No, I.
Don't do it. Right? This is really important. It's true. You could absolutely do this and you could write it out. And I think that's really good, but that's a waste of your time. If you do it for fun, that's great. But we have 15 weeks and I want you to focus on the material that matters. The material that matters is not your ability to do sine cubed. Right? And by the way, you're right. It is U sub, right? It is trig subs, but that's not, I don't care, you know?
Surprised we still have clouds.
Why? It looks like the apocalypse?
Oh, it's been worse, but the amount of smoke there is. It looks like a filter in a movie.
Real. That's
why
why
it's
It looks like the.
anytime that a white person goes to Mexico.
What?
That's the same thing I sent to my dad.
Yeah. I mean, people, all they do is they shoot in Southern California and then use yellow filter, right? So. What?
The integral from zero, sine,
This?
yes.
There you go. This one?
Part of the fifth over 5.
Part of the 5th over 5, this one? 2 pi. All right, teamwork makes the dream work. Right? And there's the hard one. Now, do we need to have done that? No. Did I do it? Yes. Hey, for me, whenever I did this a long time ago. Okay, good. No one cares. There it is. Okay, so now we have to remember another thing. How do you interpret moments of inertia?
Change spinning.
Good, very good. That's the interpretation, right? That's how we internalize it. When I write it out like this, with numbers in front of mr squared, I told you that the numbers in front of mr squared had a meaning. What are they? Good. And which numbers are more differentiated? Well, I have two answers.
I'm uncertain, so take that answer.
Okay, so what I said is the coefficient in front of the mr squared tells you how centralized the mass is. Okay, so we're gonna prove that. So this number here, 2/5, that's just what percent?
40%.
40%. Okay, so we saw an example when I first introduced this of something close to 66%. You remember what that example was?
2/3.
Yes, but that's not what I'm asking.
Oh,
What was the example? What object was I representing that was 66%?
You guys in the bathroom or nothing?
One of those is fine. It wasn't a body. This is not a real thing. Okay, we're gonna see. What? Well, they're all balls. They're all spheres. It's not real. Well, we have real ones that we can make, but you don't find them in nature. This would be the mass all concentrated in the exterior of the sphere. And you can show that too. Right? By creating a density function that's only between, say, 90% of R to R. You would do that same integral, but instead of rho, come on now. Right? So here's the R part. Instead of rho just being up here, it would be here. And the integral would be 0 from 90% of R to R. Or sorry, from 0 to 90% of R, that would be a 0 contribution, and then 90% from 0.9R to R, right? And that would boost those numbers dramatically to 66%. Okay, so you claim to understand it, right? And you could teach it to someone who wasn't here? No, neither of those are true? Good, so let's do a more complicated version. Okay. So now let's imagine that the density decreases from the surface, or sorry, from the center to 0 at the surface. Does it make sense for it to be 0 at the surface? Why?
Surface then, or is it?
Well, that's typically how we define surfaces. Right? Where does the density of the table go to 0? So currently, let's say I'm blind. I put my hand on the edge of the table, I feel the table. And as I keep moving my hand to the right, eventually my hand falls away. That defines the edge. Where the density disappears, I call the end of the object. When it's no longer the object, right? Go to 0. So it should go to 0 at the surface. That's a very standard boundary condition that we're going to use if we describe any object. Okay? Now it needs to change, obviously, if it's different, if it's differentiated at all. And usually that means more mass in the center. Okay. So here's how the mass is going to change. It's going to go from 1 minus little r over the full thing. So let's see if this works out. When little r is 0, what do I get? Excuse me? You get 1 in here, right? And it's just the core value. Okay, and then what about when little r is big R? Good, right? That's what we wanted to do. So that's the simplest way to write a linearly changing density. It's the slope of density as you move through the object. Okay? So what's the moment of inertia? You can calculate it, right? Oh, no, don't make me do a calculation.
feel like the gas giant then?
Well, this is also a fake object, but this is an approximation of a real object. Yeah, we'll see when we get that number in the front, we can see what it's most similar to. Because throughout the semester, I'm going to show you moments of inertia of actual bodies. And if you're keeping these things in mind, this is telling you how centrally concentrated they are. And when I say the word centrally concentrated, you should be thinking in your head, differentiated, right? Because if it's got a ton of mass in the center, then of course, it's very differentiated. Whereas if it's kind of got mass everywhere, then it's not very differentiated. So how would you set this up? You ready to set this up? Start at the very beginning. DI is
R squared sine squared theta.
R perpendicular squared dm, which is of course R squared sine theta. Good, dm. Now we need to be careful. What's dm?
It's equal to rho times dv.
Rho times dv. And what's rho? Ah, the new thing that we did. Okay. So it's rho naught 1 minus little r over big R dv. And in radial components,
Would be that first chunk times r squared sine theta dr d theta d phi.
very good, right? Okay, so let's say this stuff times r squared sine theta. What did you say? D theta, d phi, dr, right? Is that correct? Good. Okay. We missing anything? We're ready to go, right? Get the moment of inertia, boom. Right? Is that true? What? You still need the big M? Well, the big M is what we're gonna use. Remember, we just want that coefficient, right? So we just want to know what the coefficient of MR squared is. So I'm not that worried about that yet. There's something else that I've written on the slide that tells you that there's another step we have to do.
Oh, I guess the boundary conditions.
We will use those when we do the integration, yeah. Not yet. Okay, so we want at the very end of the day, the very end of our board, we want something that looks like I equals number sign MR squared, so that we can interpret this piece, right? Okay. We have a problem. If I give you rho in terms of little r and big R, this integral will work perfectly, and we're going to use big R in there, and it's all going to come out. What's wrong?
In terms of,
So I have big R.
in terms of,
We need this
Oh.
in terms of m. How do I do that? Minus
Put that in the solve.
You could do it that way. Let's try it this way first. Let's integrate this. Right? So if I do an integral of this one, This will lead me to the integral dm, which is of course m, very good. And that'll be equal to the integral of rho naught 1 minus r over r, and then it'll be dv, r squared sine theta, d theta, d phi, oh god, great, d phi dr, and you can calculate that in terms of r, in terms of theta naught, right? And that'll give you it in terms of m. Ta-da! Right? I won't make you do that one. So that leads us to this wonderful part. Rho theta equals what? 3m
Big R squared.
pi big R cubed. Very good. Okay, so let's look at our DI. DI integral is yeah, this is going to be I. Good. What old mess?
Just that.
Is this piece, right? M r squared sine squared. And m you have over there. We just did this, right? So it's 3 integrals. 1, 2, 3. It's the contribution from the density, which is this piece. 3m over pi r cubed. That's rho naught. Times this one, 1 minus little r over big R. Okay. Very conveniently, that's where all my r's are. Okay. So that was the rho. The dv gives you a contribution, right? That's another r squared. So let's put that in. Simple. Okay. So I could even rearrange these if I want. So that's my dr contribution. Then I have an integral from 0 to 2 pi of
With this integral, why did you incorporate r squared but not incorporate sine theta?
well, because sine theta doesn't depend on r, right?
Right.
So this is where I'm going to do either the sine theta or the d phi, depending on how you want to do this.
Oh. This one's just-
Yeah. So I moved those two so that I could treat them as 3 separate integrals, right? This is an integral of r. This is an integral of,
Theta.
well, which one is which? 0 to 2 pi.
Oh, 0 to 2 pi is fine.
Right? And then this one is
Theta.
there. Good. So what is this?
D5.
Good. You missed that on that one because you had it last time, and then you could have jumped in and had it. And this one?
Sine theta.
It's like-
Well, which one is it?
Sine theta, right? Because you're just here. Trying to do it. 0 to 2 pi.
Has the sign right up there? Yeah.
Yeah, so there's a sine squared up here times the dm. Oh, and there's an r up here that I forgot about. So there's a dm that gives me a contribution of r squared, and there's an r squared. So this isn't r squared, it's r to the 4th. Very good. And you would have noticed that when you got the units, right? Okay, so what's this one?
That's what.
Like cube theta, right? Because we have this one up here, 2 plus this one, right? All right, so we just got to make sure that we're really careful. Okay. All right. What is it?
Oh, Swanee, I didn't come here to think. I came here to be shocked by how dark it is outside. Don't look. When I get to look. I just did all that work. All right, let's do the easy ones. What's this one? This one? This one? Oh, yeah, now we're cooking. All right, what's this one? Shut up, responding.
Basically, times. And the one has. Times.
The one has nothing?
You can see, oh, it's.
Well, yeah, it's like distributing.
Yeah. So I could go in here and I could make this really annoying, right? R to the 4 and R to the 5. And you'd be like, oh, where's mine? And of course, you're right, I could pull this out. Get it? Okay, what'd you get?
And
Well, you know how I love my big R squared. So we know that we need MR squared at the end, right? So the fact that we got that is very, very good. And I'm feeling very confident. And that 2/15, I'm just like, I don't know. What do you think? I don't know. Right? Anyone else get 2/15 for that part of the integral? Remember that we will have to multiply it by these two, obviously.
find it.
Oh, you did? That was your final answer? Okay, I think we might be factor 2 off. What? This is factor 2 off. Let's see if we did it well. R to the 4, sine cubed,
Find it here.
excuse me,
Front. 2 times 2.
I don't know. What to call it.
Is it more than, yeah, not really makes sense.
Good, so what's this number, 26%? Is that bigger or smaller than 40%? Small, so what does that mean? How do I interpret this moment of inertia? More concentrated, right? More differentiated. Now, what was our internal picture? What was the density distribution? No, just like for this object that we just calculated. What did we demand of this object? How did we set it up?
It's
Right? Densest in the middle and then decreasing linearly. So of course, one, yes. The thing that you set out to do, you did, right? You proved that a differentiated sphere has a lower coefficient than the differentiated sphere. So it's more concentration of mass in the center. Right? Right? Okay, let me ask you a separate question. We said that the moment of inertia we can interpret as what? What kind of motion? Resistance to rotation. Which is easier to spin? A differentiated sphere or an undifferentiated sphere?
Differentiated.
Oh, sorry, everyone's speaking at once. Raise your hand for differentiated sphere. Raise your hand for undifferentiated sphere. Okay, no one doesn't like raising their hand. Okay, so it's in fact, everyone is right. It's a differentiated sphere because the mass is concentrated near the pole of rotation. Right? C'est bon? So if I give you a mass distribution and I ask you to calculate the moment of inertia on the homework, you'll be able to do it now, right? If I show you a body and I show you some number times mr squared, you're going to be like, snap. Oh shit, I know that that means this is how the interior is distributed, right? Sure. Okay, good. Okay. All right. I think I fucked these slides up because I was supposed to have this whole section on cratering, but it looks like it's out of order. So what's a crater? A hole. Good. It's a hole. What's special about it? Anything? What's different about craters versus lit holes on Earth? Yeah, they're made by something else. Are there any holes on Earth made by craters? Yeah, there's some famous ones. The unique thing about craters is that they're mostly circular. So volcanoes don't have any sort of restrictions on their circularity. Something like the Hawaiian Islands, maybe the caldera itself has a little bit of circularity, but they can be kind of oblong sometimes, whereas craters typically are circular. And this was a huge source of contention historically, because people looked at that and said, there's no possible way that could be from an impact. They didn't know how craters were formed. They said there's no possible way it could be from an impact because they're all circular. And you say to yourself, what the fuck? I mean, we know that they're from impacts now. So how did they get it wrong? Does anyone know? Yeah. Right. So if you throw a rock at mud, right, you make a long streak. So they were saying what? These things just come in vertically every single time and you never see any at an angle? Well, that's also wrong. What did they get wrong there? In fact, they come in at an angle more than they come straight down. The most likely angle is in fact 45 degrees. Yes. In fact, it wouldn't be until the development of what modern instrument? What? No. Something happened that has nothing to do with cratering that went, oh. The atomic bomb. The discovery of this discovery and deployment of the atomic bomb demonstrated how you could create craters on the moon. Why? Because they have comparable energies. And when you detonate an atomic bomb, you always get a perfectly round hole. Okay? So there is obviously some morphology, and we'll talk about how the excavation site varies here. But the basic phenomenon is straightforward. Object is coming in very fast. As it hits, it burrows. And as it burrows, it deposits that energy not just at the top, but into the regolith. And it can work at excavating, right? So you see that there's some excavation and there's also some folding, right? So this is A, B, C, D. And depending on the size of the crater, you can get things like central peaks, where you basically make the entire thing like act like a fluid. And just like when you are in the restroom and you feel a little water jump back up, that's what that is, right? But on craters, okay? Depending on what the object that you're hitting, you may get relaxation of the slopes. So if there's a lot of volatiles in there, let's say there's like icy like rims, and then you smack into the ice is much more likely to relax. And so the slope will go from being sharp to being very smooth, right? You'll also have melting. I hope that's obvious. Okay. And centers are lower to the ground, so they are impacts. Craters that are formed from volcanoes have this very distinct feature that they are higher than the surrounding area. So that can get a little confusing if you have like a volcano amongst like other volcanoes, you don't know where the ground floor is, but you can get better at doing that with radar, and you can do concentrations of mass, so you can see the different types of mass. Okay. So we're going to talk first about craters on the moon, then we'll look at Mercury. The moon and Mercury are very similar, and we'll talk about them in terms of like what one of them can teach us about the other and how we know that their two histories are so different, right? But we need to first talk about their primary feature, and their primary feature, of course, is the craters. Okay. This is a simulation. This is a smooth particle hydrodynamic simulation, and this is going to be the crater just before it impacts. So it's going to go in and it's going to bang. Okay. Excited. See if it works. It's better work. Okay, let's run that in really slow motion. All right. So I wish I could go frame by frame here. So you'll notice here, as it impacts, right, it's going to go in to layers of this regolith. And the way these smooth particle hydrodynamic simulations work is these are all parcels of either fluid or of substrate. And so each one of them is being modeled. And they, for example, here, right, these temperatures are going to increase. It's going to melt the object. So they can do everything in these calculations to understand what temperatures it got to, what pressures it got to. And that's really important, remember, because when we talked about when you impact an object at high velocity, you could theoretically melt the minerals that are there. And if, for example, you flung some of those minerals out, then you could look at those pieces of mineral and you would see that they were remelted at a time that was later than the rest of it, right?
Oh, like if there were,
Right? So let's say, you know, you look over here, this is going to form a crater, and you go and you pick up some pieces. You'll find out how old the crater is by looking at when it was shocked. Right? All right, so let's move forward a little bit. So it gets in there real deep, deposits all that energy, and subsequently the surface rebounds. Sorry, I'm just like stepping through it right now. You'll notice that some of this material, right? This is the shock wave that's headed down. That is not the original impact. This is energy. This is the shock wave. It's probably getting into the medium. Okay. And you'll notice that despite this is what we would call ejecta. So this is material flying off of the object after it impacts, right? Just like a billiard ball might. Watch what happens to the final configuration here as we move through this simulation. You get melting of the entire object and you excavate. Right, you can already kind of see it. Right, even though you deposit the energy here, right, you get rebounding and melting in the entire crater. And then by the time it's done, you think it's a circle. And you lose all information about the impact angle, except for sometimes the ejecta blanket can tell you a little bit. So you can look at ejecta rays. Another way you can tell which direction it came from is if there's more than one object that hit. Let's say it's a comet or an asteroid that's breaking up as it comes. You can have secondary hits. You can have one hit, and then it launches stuff and that hits. Or you can have two that are right next to each other that hit like that. And that kind of tells you which direction it came from. Makes sense?
Like that shape, you use.
Yeah, well, if it's perfectly circular, you can't tell which direction it comes from. So the crater itself doesn't tell you which direction it came from. But things like the ejecta blanket can, which is the stuff that is coming out, right? This stuff is spewing and falling down. Okay. As we look at the moon and as we look at Mercury, we'll see examples of ejecta blankets. And that is bright material that's unearthed, right? So the material on the surface is very dark. The stuff that comes up can be very bright, and then it covers the area. And you might notice some preferential directions, right? So it might look like most of it's going in that direction. And that can tell you a little bit about how the thing formed. Right? And of course, if it has an atmosphere, that's even better because that pushes that material. Okay, and let's talk really quickly about ages here. Most of the moon's craters are very old. They can be seen to be overlapping with newer craters, right? The moon is basically our best clock for the uninterrupted 4.3 billion years since it's been around. Right? So planetesimals around the solar system get less abundant as they get swept up. So what that means is you aren't having small planetesimals be replenished by any source unless you break up some big object. Okay? So most of that happened in the early solar system. And so as you start eating up little things, you run out of things. Okay. And so we'll look at the size frequency distribution of small craters when we get to small bodies. And we'll notice obviously a correlation there. But what we can say is the more heavily cratered surfaces have to be older than the smoother ones. Okay. So what do we mean by older there? Yeah, what does a surface being old mean? Untouched by what? What is it? What do we mean by old? New generation of surfaces, right? So for example, if you have continental crust and you melt it, it's no longer millions of years old. It's new, right? If you have continental crust and you put a landslide on it, it's new. If you have continental crust and you flood it and you erode it, it's new. It doesn't have those old markers on it. Okay. Does that mean that the Earth is not as old as the moon? No, just the surface. So this is called resurfacing. So surface ages and compositions are different, right? The body might be just as old as the rest of the solar system, but the surface in a particular location might not be. Good. Okay, so, oh yeah, this is completely wrong. I need to update all the words there. We already did for US stuff. Okay, so let's go back and start looking at the moon. So here's the moon. Oh fuck, bro. Okay, sorry, I was going a little fast. Here's your basic facts. Moon, not big. You know what this symbol is here? Earth mass. How much of the Earth's mass is the moon?
1%.
About 1%, yeah. Is that surprising to you? Yeah, that's pretty surprising, right? You think of the moon as big. We are bigger by a lot.
So close.
Well, yeah, it's definitely close. Yeah, it's the closest thing to us, thankfully. And you know, the interesting thing is look at this mass, or sorry, look at this radius here, right? 2%, right? 27%? Oh, yeah. Well. So it's about the quarter of the physical size. Okay, and here's your density. Well, how do we interpret that? Rock. Good. Very good. It's rock. Good. What's this one? What's that word? How shiny? Moon shiny? Not shiny. Wait, which one is? I heard very shiny. Okay, but doesn't everything reflect sunlight except for like Vanta black? What's what? Albedo. Albedo is the albedo. So albedo is how reflective you are. So what's the albedo for snow? It's almost 1. It's like 0.9. Clouds are like 0.9. What's rock? That's between 0.2 and 0.3. I know, that's really disappointing. So this is 0.12. Prismani, are you lying towards us? Because it's big, it's close. So in fact, most of the sunlight goes into heating the surface. About 87% of it goes into heating the surface. The moon is very gray and it's very dark. And we can go back to the very beginning and I'll show you those pictures. If you look at just moon rocks, they're gray. They're not bright like they should be. But the problem is you don't have any context, right? You don't know what that looks like. You're not standing on. Okay, surface temperature. Cold, very good. How long it takes to go around us? 28 days, good. Moon, month, we already got that. Okay, moon's leaving us. Says that we haven't been really good friends to it, and it is heading away at about 4 centimeters per year. How do we know that? Good. How do we measure the distance to the moon? Good. What lasers do we use? Very good. Okay, so there is a very cool mirror. You take a mirror like this, right, and you bounce towards it. You know, if you bounce at this angle, it's going to bounce over there. If you take 2 like this, you can see what you look like, right? Because if you take like this, it's going to flip your picture back. If you take 3, then no matter which direction you send the laser in, you'll get it back in that exact same direction. So we put a bunch of these 3-sided mirrors that look like the edges of a box on the moon when we landed. We just set them up. Said, okay, whatever, weirdo scientists, fucking with your mirrors. And we don't have to worry about them getting too dusty because there's no air atmosphere. So you just stick it on the surface and we still use it to measure the radar range. Okay? So that's the recession rate. And it's also the distance to the moon. Distance to the moon is very important to getting, of course, astronomical distances. Here's a side that you know and love. Okay? Actually much more similar to what you would see. Right? This is the true color. And here's your crater, right?
big ass crater, and then all that white stuff, that's the ejecta. Now,
I was gonna ask, do you know what part of the movie that we landed on?
I'll show you that in a few seconds. Yeah, we landed a lot. So you can see this one, you can see this one, you can see that one. You can see, oh, you can see these little ones here. Some of them have bright ejecta blankets, some of them do not. Surface of the moon, heavily cratered. You might say to yourself, wow, that looks like a big old circle. What's that? Yeah, and what is that from? From a crater. Big ass crater. Okay? Big ass crater, big ass crater, big ass crater. So big, in fact, that it weakened the crust. And magma just seeps directly through the crust. So it's a form of volcanism, sure. This would have been like a lava sea, but the reason for it is impact. Okay? All right. This is the side you know and love. Oh, by the way, that has a name. That's Tycho. And then this is the side you don't know and love. Oh, wait, hold on, sorry. All right. If you look inside of this thing here, you'll see these tectonic features called rills. These we'll talk about a little bit more in detail when we see them on other objects, but I want to show you the far side. Yeah, let's go to the far side. There's your Apollo landing sites. Notice your Apollo landing sites are all on the near side. Why is that?
Because you don't know what's that? It'd be cold.
So I heard light. I heard easier to get to. Light, the whole moon. Let's go back. The whole moon gets lit by the sun at different points throughout the year. Near and far does not mean light and dark. Right? Light and dark is a rotational phenomenon. As I rotate, I see the sun, you, and then I don't see the sun. The moon is rotating. So you get full days and nights there. They're just 28 days long. Easier to get to, the moon is very hard to get to. It is very far away. So getting to the near side or the far side of the moon is irrelevant. Once you're there, because it took you 8 days to fly in a spacecraft to get there. 8 days, which is fucking crazy when you think about it. Okay, so that's not the reason. What's the reason? What? Okay, you're almost there. He said he wanted to set up mirrors. Because we can't talk to them. They go on the dark side of the moon. They don't have any ability to contact us. And they can't be up there on their own. Right? What if something happens? We would never know. So even when astronauts used to go behind the moon, you would have many minutes where everyone is just freaking out. They're like, well, we really hope they went around the moon, they come out the other side, and then they would reestablish contact. There's a wonderful discovery series called When We Left Earth. I deeply encourage you to watch it and just watch like the 3rd episode, like when they actually are going around the moon. Also consider Apollo 13 if you don't have the full documentary in you. Apollo 13 is very good. Talks about all of the dangers of going to the moon. And of course I think it won an Academy Award, or at least it was nominated. Okay, so that's all the landing sites. 11, 12, 13 is obviously not on there. They didn't land. 14, 15, 16, 17. What? What? I'm sad. Yeah, my favorite story for Apollo 10, you know this one? Maybe I've told this already. So for Apollo 10, they purposely did not give them enough fuel to land on the moon. Because it was the first time that they would go and they would do an orbit around the moon and then come back. And the reason they did that is they said, listen, you guys are test pilots, you're brave, you're daring. If you decide to go land on the moon, you can't get off. So you'll be the first person on the moon, but you'll die there. Okay, cool. These were sites that were planned. So 15 was supposed to be here. They changed it. But then when they canceled 19, 18, and 20, then they moved this one over.
What were they supposed to have for first?
I think that was just where the 14 was. Okay, and sorry, going over, but this is the far side. What? Yeah, so this is pretty cool, right? So remember we talked about whether or not there's light, certainly light. This is Apollo 16. They took a photo. What do you notice? Yeah, there's a couple dark ones, right? Two large dark ones, but yeah, mostly it's very cratered. We'll talk about this in the context of tides and how mare forms. But if you showed someone a picture like that, you would almost invariably, no one would say that was the moon, right? Yeah. And that's the moon.
I always forget there isn't like one side of the moon that stays dark, this is the moon on sun.
What?
You know, how your head or something.
Yeah, I know what you're talking about.
Oh, dark side of the moon? Yeah. Yeah, that's a misnomer. We didn't need Mulan for its science acumen. Yeah. You know, it just if it's a far side of the moon. Mysterious as the far side of the moon. Maybe I should ask, like, write an email, you know. You're messing up the kids. Okay. Any questions, comments, concerns? All right, folks. Try not to melt out there.